come see me. I'm more than happy to meet with you. My computer system is a little slow in getting started, kind of like me today. Hope everybody had a good break. Was that a yes? Was that a good yes, or was that a bad yes?
Great yes.
A great yes. Dare I ask what what that meant? Okay, I won't ask. I think I may have told a couple of you guys, I actually performed a wedding yesterday. First time I've ever done that in my life, and that was a cool thing. So it was done in verse. I wrote the whole thing in verse and sang I didn't sing a song, but I wrote a song for it, and we had a great time. And they ended up married, so everything worked out. One of the things you worry about when you're responsible for it is, oh my God, what's going to happen here? So, all right, let's see if we're on here. Yes, we are on. There's a lot of responsibility, let me tell you. Okay, let's get this guy going and get me going, and we're set. So today we're going to talk about a new topic. We're going to start talking about carbohydrates, and I'll remind you that we have an exam coming up on Monday. So we'll be crunching through this fairly rapidly. A lot of what I will talk about today will be review to many of you because it's material that you've learned frequently in organic chemistry. But I'm going to take us through all of this so that we are all on the same page. Okay? And come on. There we go. And every time it decides to rearrange itself, so that's fine. Okay, so carbohydrates. What are carbohydrates? When we talk about carbohydrates, we all hear that term. We all have a pretty good notion of what that is. We're talking about things related to sugar, and carbohydrates are all compounds that relate to various types of sugar. The word carbohydrate literally describes what a sugar is. Carbon, meaning carbo, and hydrate, meaning water. And if we look at the structure of simple sugars, we discover that that accurately describes them. So for example, the structure of glucose is C6H12O6. All right? We could write that as C, okay, with an X, and then H2O in parentheses with an X. C6H12O6. All right? So it's carbon hydrated is what it is. That's what a carbohydrate is. That's where the word comes from. Another term that we hear associated with carbohydrates are saccharides. And saccharide comes from, I think it's Greek, I'm not sure of that, the derivation meaning sweet taste. And so when we talk about saccharides, we talk about monosaccharides, we talk about disaccharides, we talk about polysaccharides. We're talking about things that have a sugar base of some sort. So that's really where all these things come from. A lot of what I'm going to talk about today is nomenclature. And as I say that if you're going to walk the walk of something, you have to talk the talk. And so in order for you to understand carbohydrates, we all have to be talking the same language. And so I will spend a fair amount of time talking about the language of carbohydrates. Anna, in recitation, is also going to be doing that. And I just realized I didn't check the camera, so I better do that before I discover the camera's pointed the wrong direction, which I've been known to do also. No, it's not bad for me. Zoom it in a little bit. Okay. All right. So we're going to walk the walk by talking the talk. So let's start talking that talk. When we talk about carbohydrates, we discover, first of all, that we encounter two categories of carbohydrate. We have things that are called aldoses and things that are called ketoses. First of all, whenever we see the letters OSE on the end of a name, it refers to a sugar. So a ketose is a sugar that has a ketone bond, and an aldose is a sugar that has an aldehyde bond. So we see sugars that are both aldehydes or ketone, or either aldehydes or ketones. The very simplest sugars are what you see on the screen here. All right? They both have 3 carbons, and the one you see on the left is a ketose. It's a dihydroxyacetone. We'll see a related compound later when we talk about glucose metabolism. And the other 2 we see are related to each other. We see D-glyceraldehyde and we see L-glyceraldehyde. And as you know from your organic chemistry, that when you have a carbon that has 4 different groups attached to it, they can be they can be arranged in three-dimensional space in two different ways. We call those the D form. We call those the L form. We saw this with amino acids. And now we see it with carbohydrates. We will see it with carbohydrates in more complexity than we saw it with in amino acids. But there's a very saving grace. Biochemists like myself are very lazy people, so we don't worry overly about those configurations. And you'll see, I shouldn't say we don't worry about them, but we don't have the naming concerns that chemists have for them. And so we'll see how that plays out as I'm talking about it. Again, reiterating, we see this is a ketone, carbon with two other carbons bound to it. We see this is an aldehyde here, where we have one carbon bound to a carbon here. Aldehydes, as we learn in organic chemistry, are chemically more unstable than ketones are, and that plays a factor in one of the considerations we will have for them. Another way we could describe these compounds, they each have three carbons, is we could describe them as what we call trioses. Tri referring to three, and all three of these compounds you see on the screen are trioses. Okay? Well, that triose nomenclature brings up what is related here. A monosaccharide, first of all, is a sugar that has one unit. Instead, we'll see disaccharides where we start linking units together. But all these are monosaccharides. And we see that we could call something with three carbons a triose. We can call something with four carbons a tetrose. We call something with five carbons a pentose, a hexose, a heptose, an octose. Generally, we don't see monosaccharides larger than octoses. That's about as big as the monosaccharides themselves get. Now the question then immediately arises, well, do I call it a triose or do I call it an aldose or whatever? Well, we can actually combine those names. So we can refer to something as an aldotriose, for example. If you decided to call it a trialdose, all right, I probably wouldn't count you wrong. You've got the right idea there, so I'll give you credit for the idea. But you'll see that there's various ways that we can categorize those sugars, and we can frequently add those names on. So an aldotriose would tell me it was both an aldose and a triose. So that would be either L-glyceraldehyde or D-glyceraldehyde. Okay, now I'm going to show you a whole bunch of structures today. I'm not going to hold you responsible for most of them. I will tell you which structures I think you should memorize. There are some structures, and I don't believe in memorization just for the sake of memorization. But there are some structures that I think you should memorize because you will see them in other classes besides this one. And I will tell you those as we go through. There's only a handful. All right, so I try to keep that to a minimum as much as I can. All right, well, as we look at sugars, when we have asymmetric carbons, we discover that we can, in fact, oh, come on. Why do you want to do this to me? Oh, I lost my connection. Well, I guess I'll control it over here for the time being. I'm not sure why it did that. Nope, there it is. Maybe the computer doesn't like the weather either. Okay, there we go. All right, so we discovered that we have that arrangement of four carbons. Well, I have a connection, but I have no mouse. Oh. Now I have a mouse. Okay, that we can have mirror images of each other. Okay, so an L-glyceraldehyde, for example, is a mirror image of a D-glyceraldehyde. All right. All right. Now, this starts showing us the complexity that we can have when we start adding other carbons that are each themselves asymmetric to that one that we had in L-glyceraldehyde or D-glyceraldehyde. If we start at the top with D-glyceraldehyde, for example, and we add another asymmetric carbon, that other asymmetric carbon being added here, okay, we discover that now we have D-glyceraldehyde can exist in two forms, one form here and one form here. Look how they differ from each other. One form has both hydroxyls on the right side. This form has one hydroxyl on the left and one hydroxyl on the right. These are chemically different from each other. They both are aldoses. They both are tetroses. They're not mirror images of each other, because if they were mirror images of each other, we would see both of these guys being on the left side. So what I've just shown you is something that are molecules that are stereoisomers, meaning they have different stereo configurations. But because they have the same chemical structure and they have the same number of carbons and they're not mirror images, we call them diastereomers. D-I-A-S-T-E-R-E-O-M-E-R-S. So these two guys are diastereomers. They are not mirror images of each other. I want to underline that. Okay? They are not mirror images of each other. Now I'll talk about mirror images in just a minute. There's nothing on this screen that you're going to see here that is a mirror image. Okay? What we're taking is we're adding one carbon each time to an existing D sugar and showing the possible configurations that that carbon can have. Well, if we added one asymmetric carbon, it can have two different configurations. If we add two asymmetric carbons, they can have four different configurations. If we add three asymmetric carbons, they can have eight different configurations, blah, blah, blah. Okay? These are just the D isomers. When we think of the L isomers, we've got an entirely other set of all of those. So for example, if I take into consideration all of the L isomers, I will have, if I have 6 carbons, I will have 8 additional L isomers, or a total of 16 different stereoisomers of this sugar, of this aldose. I'm sorry, of this hexose. I can't talk. Of this hexose. Well, what does a hexose have? It has 1, 2, 3, 4 asymmetric carbons. The number of possible configurations of D plus L will equal 2 to the 4th. 2 to the 4th is 16. If I have 3 asymmetric carbons, 2 to the 3rd is 8. And so I've got 4 plus 4 other L's. I'd have a total of 8. So I add 2 for every asymmetric carbon, or I multiply by 2 for every asymmetric carbon that I add in a saccharide. Okay. Well, I said something about enantiomers and about mirror images. I need to give you some thoughts about that. If we look at the original guys up here, we see that we have D-glyceraldehyde and L-glyceraldehyde. I wish I had that written in a better way I could show you. Let's see. Let me see if I've got that. Okay. I think it's later. I apologize. This is showing you the corresponding structures that I would have if I have the ketoses that I start with. So instead of starting with L-glyceraldehyde or D-glyceraldehyde, in this case I start with dihydroxyacetone. You'll notice dihydroxyacetone does not have a D or L because dihydroxyacetone has no asymmetric carbons to start with. If I add one asymmetric carbon to that, I create 2 possible structures. Okay? I only see one of them here because I'm only seeing the D. I'm not showing the L, so the L would have another structure. The L would look just like this guy, except for it would have the hydroxyl on the left side. That would be a mirror image of D-erythrulose, and that mirror image of D-erythrulose would be called an enantiomer. So 2 molecules that are mirror images of each other are referred to as enantiomers. Doesn't matter if they're ketoses, aldoses, as long as they are mirror images of each other, they are called enantiomers. Okay. Well, we started with 1 fewer asymmetric carbon, but each time we add another asymmetric carbon, again, we're going to multiply by 2 the number of possible configurations that they can have, and we get to this up here. Now, well, I said a lot about structure. I said I was going to make you memorize some structures. I'm going to point out to you on this figure and the previous figure which structures I think are important that you should know for an examination. Okay? One is this guy right here, D-fructose. One of the most abundant sugars on the face of the earth. We will see it appears in several metabolic pathways. It is half of what we talk about table sugar. We talk about sucrose. Sucrose is a disaccharide. It has 2 different sugar molecules in it. One of them is fructose. The other one is glucose. What I'm showing you right now refers to what's called the straight chain form of the sugars. I'll show you a ring form of these as well, and you are responsible for both the straight chain and the ring forms of these various sugars that I'm describing to you. So you're responsible for straight chain and ring of fructose. Okay? That's the only ketose that I expect that you're going to memorize. When I look at the aldoses, there are several, okay? So the aldoses that I think that you should know include the most common sugar on the face of the earth, and the most common sugar on the face of the earth is right here, D-glucose. You should also know the structure, okay, of D-galactose, which is over here. This is a component of what's called milk sugar or lactose, and I'll talk more about that later. And you should also know the structure of D-ribose. Ribose is what gives the R part of RNA, ribonucleic acid. The ribo part arises from the fact that the sugar in RNA is known as ribose. Notice that ribose is a pentose. These guys are, all the other guys I asked you to know are all hexoses. Yes? The sugars are D-ribose, D-glucose, and D-galactose. And you're saying, well, you're only doing the D's, how about the L's? All right? Well, I'm going to tell you a very simple rule for the L's in a second. It turns out that in nature, the vast majority of sugars that we see are in the D configuration. It's not as absolute as amino acids. All right? There are some sugars that exist in the L, but the vast majority of them exist in the D configuration. Okay? The biologically relevant ones, certainly almost all, are in the D configuration. Okay. Well, how do I get L-glucose if I have D-glucose? Well, first of all, we need to understand what gives D-glucose the D part of its name. Right? When we look at the D, let's look at the common feature that all these guys have. Notice the carbon one up from the CH2OH. Notice that in every single case, that carbon has its hydroxyl on the right side. The next to last carbon has the hydroxyl on the right side. That's actually what gives the sugar the D part of its name. Okay? And you might say, oh, well, then it's very easy. If I want to know the L, I simply have to take, for example, D-glucose and move the hydroxyl to the left side, and the answer is no, it's not. Okay? L-glucose, if you want to underline something, L-glucose is the enantiomer of D-glucose. In fact, the L of any sugar is the enantiomer of the D sugar. So, for example, if I wanted to write the structure of L-glucose, I would have the following. Carbon number 2, which is this carbon right here. There's carbon number 1 is the aldehyde. Carbon number 2 is right here. Carbon number 2 would have the hydroxyl on the left. 3 would have hydroxyl on the right. 4 would have hydroxyl on the left. And 5 would have hydroxyl on the left. In other words, it has to be the exact mirror image before I can call it L-glucose. You will be amazed at the number of professors, even in biochemistry, who don't recognize that. I discovered that difficult way talking to some of my colleagues. Okay? It's not just the last one. It's actually the mirror image of the entire thing. Everybody got that? So, if you know the D configuration, you automatically know the L configuration because it's the mirror image of the same thing. If I asked you for L-ribose, you would simply say, oh, well, it's got carbon number 2, hydroxyl on the left, hydroxyl on the left, hydroxyl on the left. L-ribose is very simple. In fact, all these are very simple once you know the D sugar as such. Okay, now, well, are all these other sugars important? The answer is we see these other sugars appearing, and there we go again. Why is that doing that today? We see these sugars appearing as minor components of many metabolic pathways. Probably the most prominent of these right here is D-mannose. And D-mannose, as we will see, is important when it comes to trafficking of things inside of the cell. Okay? So mannose is important. And all the others appear in various other configurations. Sorry for all that. I'm not sure what the computer's doing today. Okay, questions about that? Nomenclature, structure? Yes, sir? Nope, I'm not asking you no D-mannose, no. But galactose, glucose, ribose, fructose. Okay, well, let's go back to here and talk a little bit about cyclization of sugars. I'm sure in organic chemistry you learned some of this, but I will remind you a little bit of what's here. If I take an aldehyde and I combine it with an alcohol, as we see here, I can create something called a hemiacetal. And that becomes relevant when we talk about the cyclization of aldoses, because we have an aldehyde. And that aldehyde is coming around and interacting with the alcohol at carbon number 5 most commonly, as we will see. If I, instead of having an aldehyde, I have a ketone that reacts in a similar fashion, what I make is something called a hemiketal. So there's a ketone reacting with an alcohol to make a hemiketal, and that happens in the cyclization of the ketosis. Well, the cyclization, as we can see, generates some compounds that I'm going to introduce another nomenclature for in just a second. Okay? All right. The cyclization of the sugars, as we will see, generates compounds that look like these two compounds. Purane is a 6-membered ring. As you can see here, it has a single oxygen in the ring. Furane is a 5-membered ring, and it also has a single-membered ring, oxygen in the ring. Okay? Now, these two guys give rise to names that we give to sugars that form 6-member rings or 5-membered rings. I'll come back to that in just a second. Okay, so keep these names in your mind, purane versus furane. Okay. Oh, blast it, what's it doing? I think this doesn't like the heat today, is all I can figure. Okay? Well, how do these things happen? How do they form? Okay? Well, this is a very nice figure because it shows, when it's actually showing, it shows how that cyclization happens. We see on the left glucose being present in the straight chain form, as you can see here. And we see interaction between carbon number 1, the aldehyde group, and carbon number 5, shown right here. There's the alcohol. So this guy is forming a hemiacetal. And we can see that cyclization sort of happening in the process here. And this now shows us the final structure that we get. Notice it's called a glucopyranose because it looks like that purane molecule that we had before. The purane was a 6-membered ring that had a single oxygen in it. So this resembles that, and we call it, as a consequence, a pyranose. Now, notice we have two different possible structures. And the reason we have two possible structures is we have just created a new asymmetric carbon that didn't exist before. We have a new asymmetric carbon that didn't exist before. The asymmetric carbon is at position number 1 in this case. And the asymmetric carbon that forms on cyclization will always involve either the aldehyde, if it's an aldose, or the ketone, if it's a ketose. This is an aldose, so we see carbon number 1 being involved. Carbon number 1 becomes asymmetric. It wasn't asymmetric before because carbon number 1 before only had 3 things attached to it, not 4. Now it has 4 different things attached to it, and the attachment of those 4 things to it causes it to be asymmetric. That means that the hydroxyl that is on that carbon can be in 2 possible configurations. We draw them in the structure here as either the up or the down being called the alpha, and that's what the alpha refers to right there. If that hydroxyl is in the upward configuration, we call it as beta. So alpha or beta configurations arise as a result of cyclization. If we don't have cyclization, we will not have an alpha and a beta because, remember, without cyclization, that carbon is not asymmetric. So it's important to recognize that that cyclization is causing that to happen. Now you'll notice that both the going to the up or the bottom, the top or the bottom, okay, going to either the top or the bottom is a reversible reaction. That's what we see is happening, if we saw it happening. That's what we see is happening with these arrows right here. Okay? Well, what does that mean? It means that if we are in solution, that is, we have this material dissolved in water, that we can go between glucopyranose and alpha D-glucopyranose and beta D-glucopyranose. We have to go backwards through this intermediate and go back to here. Okay? So ultimately what it means is we have to be able to go to the linear form. But if we can go backwards to the linear form from here to here, it's possible then to go back down to here. Now I mentioned that because you say, well, of course it's possible. There it is. Well, I'm going to show you some chemical modifications in a bit that will prevent going backwards to the linear form. And if you're prevented from going backwards to the linear form, you cannot change from alpha to beta or from beta to alpha. It gets locked in a configuration. That becomes important for our consideration later. Okay? So for right now, the fact that there's nothing blocking this from happening means that we can go backwards and forwards between these different forms. And in solution, that happens all the time. Alpha to beta, beta to alpha, etc. It turns out that solutions tend to prefer the alpha a little bit over the beta. There's more things found in this configuration than there are in this configuration, but both are possible. Okay. If we cyclize fructose, fructose is of course a ketose. What we see is something like this. They only show us one of the forms here, which is kind of dumb. I think your book does that, but your book doesn't always do things I think are smart. There is ketose. Remember that we said that the cyclization involves either the ketone or the aldehyde, so there's the ketone part right there, carbon number 2. In this case, it also interacts with carbon number 5. It makes a 5-membered ring. And that 5-membered ring, in this case, they're showing you alpha D fructofuranose, because this guy looks like furan, that 5-membered ring with the single oxygen atom in there. Notice that this is the alpha configuration. The alpha always refers to the position of the hydroxyl off of this new asymmetric carbon. Well, the new asymmetric carbon has a name. That name is called the anomeric carbon. The anomeric carbon is the asymmetric carbon that's created by cyclization. The anomeric carbon, or I'm sorry, the asymmetric carbon that's created by cyclization. Why don't they show the beta? Can we have the beta? The answer is yes, we can. Why they chose not to put it here, I don't know. But if we had the beta configuration of this compound, what we would have is we would have the hydroxyl up, and we would have the CH2OH down. Yes?
Is the alpha configuration favored because then they can bind to more monohydrates?
No. So the favoring of the alpha versus the beta has solely to do with steric hindrance. Okay? So that's the only difference, because these are just chemically happening routinely in solution. Yep. Okay? Now, it's fructose that students frequently confuse when they draw structures. Don't forget carbon number 1. Okay? You didn't see, in carbon number 1, aldehyde was, the carbon number 1 was the anomeric carbon in glucose. The anomeric carbon in fructose is carbon number 2. That means you've got another carbon to keep in mind. So whenever you draw a structure, I always recommend that you number your carbons so you don't get confused. There's carbon number 1, there's carbon number 2, there's carbon number 3, 4, 5, and don't forget number 6. Okay? If you're drawing a structure of fructose and you know it's got 6 carbons and you've only got 5 of them on your structure, you'll know that there's something wrong, right? Okay. So that cyclization gives rise to this. Okay. All right. If we look at ribose versus deoxyribose, we most commonly write it in the ring structure, which is what you see here. Ribose is very simple in the ring structure. When we look at it in the ring structure, this is known as beta-D-ribose. Alpha exists as well, but in biology we see it almost always in the beta because it's found in nucleotides locked in the beta. The ribonucleotides, ATP, GTP, CTP, UTP, all have ribose as their sugar, and the ribose is always in the beta configuration for them. The related sugar, beta-2-deoxyribose, is the modified sugar that we see in DNA. And that's the D part of the DNA, deoxyribonucleic acid. The difference between the ribose here and the deoxyribose is shown by this oxygen present at position number 2. And though that seems like a very minor difference, it turns out to have great significance for the chemical stability of RNA versus DNA. DNA is far more chemically stable than RNA is, which is probably why that evolved in the first place. And as a consequence, we can isolate DNA samples that are thousands of years old and still get information out of them. We can't do that with RNA because RNA will break down over time. And the difference being solely that single oxygen right there. Okay, so I'm frequently asked this question, so I will show it to you, but you're not responsible for it, okay? Can fructose form a pyranose? Yes. Can glucose form a furanose? Yes. But both of those are very minor forms. I'm only showing you this not to make you responsible for it because you're not responsible for it, but just to show you what they look like if they make that structure, okay? Notice that in the case of fructose, we make a 6-membered ring. That's what it takes to make a pyranose, okay? But carbon number 6 is actually this carbon right over here. There's no up or down carbon apart from that, okay? This is what it looks like in this configuration here. One of the questions I also frequently get at this point is, well, what does the L version of this sugar look like, okay? Well, the L will literally be a mirror image of what you see here. We will have the CH2OH down, we'll have the OH up, we'll have that down, and we'll have these two guys flipped over here, okay? So the L, one of the ways you can spot an L sugar in a ring is the L sugar will always have that carbon down, that last carbon that would normally go up here. Okay, I'm kind of going through that kind of fast. I know it's kind of review for many of you. Any questions on that as I'm going through it? Or as I now have gone through it? Anybody awake? Nobody's awake. Okay. Well, I'll try to stay awake because one of us has to be awake at least. All right, so let's talk about some conformations that sugars can have. I've already referred to steric hindrance in one case, and so I want to give you a sort of classic example of steric hindrance. We're not going to focus on it too much, but we remember that we can't put atoms together too close together in space. They don't want to join up with each other. They don't want to be overly close in orientation. So we have to take some of these considerations of steric hindrance into account. We can imagine as we look at a sugar, we got all these groups above and below the ring, for example, that these groups might interact with or might interfere with each other, or there might be some effect on the overall structure. And the answer is, well, in fact, there is for many compounds. One of them I'm going to talk about are the boat and chair configurations of glucose. Okay. Now, what you see on the screen are two different representations of exactly the same molecule. Both of these are beta-D-glucose. Okay? Both of these guys are beta-D-glucose. The difference being that they have sort of shifted the bonds, not to change the up or downness of the hydroxyl groups, but they've shifted their bonds to position the groups as far away from each other as they can. Okay? These two guys right here are relatively close to each other in three-dimensional space. They will avoid that as much as they can. They're not impossibly close. Otherwise, we wouldn't have this possible configuration. They're not impossibly close, but they really prefer not to be close to each other. I'm sure you've probably been around people who don't wear deodorant, and though you may not be impossible to get close to them, you may not want to hang around them an awful lot. All right? Well, these two groups don't like to hang around each other as much as possible. So what they do is they do what you do around that person with no deodorant. You sort of keep yourself a safe distance away. Okay? Well, that's what these groups are doing. They're simply switching, and there's some flexibility in single bonds, you remember. They're simply switching that flexibility to convert themselves from the unfavorable configuration, which is what we see right here, to a more favorable configuration, which is shown over here. You can see over here that this hydroxyl has essentially shifted outwards instead of being upwards. And that required a shifting of the positions of these bonds between these carbons and this oxygen over here. This configuration had those positions in the upward position, and over here they're in the downwards. It didn't change, again, the overall structure. These are both beta-D-glucose. The conformation, the arrangement of these atoms in three-dimensional space changed. The structure that we see on the right, as it's labeled, is called the boat form, because if we trace the position of the carbons and that single oxygen atom, we see that they go down, across, up. It looks sort of like an odd little canoe, okay? And we call it the boat form. The chair form over here looks a little bit more like a chaise lounge, okay? Maybe you just spent some time on a chaise lounge over the weekend, sitting there. There's the back of the chair right there. There's the butt part, and there's where you're hanging your feet down over here, okay? So boat versus chair, it turns out that not surprisingly, based on what I've told you about steric hindrance, is that when we look at this, structure of glucose, we find that the chair form is actually preferred and the boat form is disfavored. We can find, and we do find some things in the boat form, but for the most part, the boat form is not very favored. Okay. We see similar things with 5-membered rings. They're a little bit more complicated to understand, as you can see here. I sort of think about these as sort of envelope structures, but even there I have a hard time envisioning them in my head, so I figure if I have a hard time seeing them in my head, why should I make you do them? So I won't. Okay. All right. So those are general structural considerations that we have for monosaccharides. I want to spend a little bit of time talking about chemistry of the monosaccharides because they're important for us to understand as well. Okay? So these processes I'll be talking about first involve oxidation. And oxidation is an important consideration for us with respect to monosaccharides. Oxidation, you remember, is the loss of electrons by a compound. And so what we see on the screen is a reaction that's involving the oxidation of glucose. Glucose, you remember, is an aldose. And from your organic chemistry, you remember that aldehydes are, in fact, the most readily oxidized compounds. This aldose is not a very stable structure. Okay? Chemically, it's very easily oxidized. When you oxidize an aldehyde, you get a carboxylic acid, which is what we have on the right side. Okay? And if we ever oxidize something, every oxidation, of course, involves a reduction of something else because a compound being oxidized is losing electrons. Those electrons have to be grabbed by something else. In this case, the electrons are being grabbed by copper. Copper is being converted from +2 to +1. That creates cuprous oxide. And most notably, that involves, if we have copper +2 dissolved in water and we change it to copper +1, the color of the solution will change. We can actually monitor this process by monitoring the change in color of the solution. Okay? Copper is an oxidizing agent, as you see it here. An oxidizing agent gets reduced. A reducing agent gets oxidized. So you can gather then that glucose is a reducing agent. It donates electrons to something else, causing something else to be reduced. In the process, it itself becomes oxidized. Now, if we tried the same reaction with fructose, fructose is a ketose, we discover it might go to a limited extent, but for the most part, it doesn't go at all. And that's consistent with the chemistry that we know about ketones because ketones are chemically stabler than ketones are chemically stabler than aldehydes are. Therefore, ketoses are stabler than aldoses are. And we see that ketoses are not very good reducing agents. Not very good reducing agents. Okay. Now, if we examine some other chemistry that can happen, what you see on the screen here are two different modified forms of glucose. They are both glucopyranoses, meaning that they have both been in the ring structure, but they've been modified, and the place where they've been modified is the anomeric carbon. Instead of having an OH, we have an O-methyl. Now, this illustrates a very important principle. Okay? First of all, we've just created something called a glycoside. A glycoside is a molecule, okay? It's a sugar that has had its anomeric carbon altered. It is the hydroxyl on it altered. All right? This hydroxyl on the anomeric carbon got altered. That's what made a glycoside. The top one was altered in the alpha configuration. The bottom one was altered in the beta configuration. And, this is important, once I alter it, it can no longer go back into the linear form. Now, my question to you at this point is, would either of these sugars be reducing sugars? Should I save that for the exam? Should I do it for a pop quiz? What do you think? Reducing sugar or not a reducing sugar? What does it take for something to be a reducing sugar? Has to be an aldehyde, basically, right? Okay. Is a ring structure an aldehyde? What does it take to get out of a ring structure? I didn't tell you that, did I? Okay, so I'll tell you the last part of the puzzle. The last part of the puzzle is it takes an OH. Once they alter that OH on the anomeric carbon, it can't go back to the straight chain, which is where I had the aldehyde. These guys are not reducing sugars. They cannot be reducing sugars because they cannot go back to the linear form. And if they can't go back to the linear form, what does that tell you about their configuration? It's locked. So once I've made something in the alpha configuration, it's going to stay in the alpha configuration. It cannot flip into the beta. I had to make these guys separately. I couldn't expect them to flip in solution. Once I made one, it was stuck in that configuration. Did you have a question? Oh, you're just doing your hair. Okay. Okay. So glycosides, we will see, are not just chemical curiosities, but we'll see that the way that sugars get linked one to the other to make things like starch, or to make things like cellulose, or even to make things like disaccharides, they're almost always made as glycosides. So this modification that we see here is a simple chemical modification, but we'll see that the joining of sugars actually creates glycosides. Okay, here are some other glycosides that we can see in cells. This is a modification that completely changed the OH. It changed it to an N linked to something else. So that's a nitrogen. We'll see that a commonly modified form of sugars involves what's called N-acetylation, putting a nitrogen on there, followed by an acetyl group and other things like that. So there are many different glycosides that we can envision. Okay. And what was this? I can't remember. Okay, so here are some unusual and modified sugars, okay? They're unusual. How are they unusual? Well, again, I'm just showing you these. You don't need to know these or memorize these. Here's fucose. Look at the carbon up there. It's a CH3. Doesn't even have an OH on the end of it, okay? Here's acetyl galactosamine. Here's a modified, not an anomeric carbon, but a carbon number 2 that's been modified there. This guy here is important in glycoproteins. This guy over here, beta D-acetylglucosamine, very important in things like making chitin, the exoskeleton of insects. This guy here is an important molecule, as we will see later, in signaling. And yeah, that's pretty much it. You'll notice also that this guy was in the L configuration. I said in the L that the carbon went down, not up. So you see the methyl group pointing down there also. Okay, the last modification I'll mention here, and I only mention it here because we will talk about it in a couple of days, and that is phosphorylation. We talked about phosphorylation relative to proteins, and we said that it changed the behavior and the activity of proteins significantly by changing their charge. So too does putting a phosphate onto any of these compounds change their chemistry as well. Putting a phosphate onto any of the sugars basically creates a higher energy molecule. Basically creates a higher energy molecule. We'll see glucose 6-phosphate is important in the breakdown of glucose. We'll see dihydroxyacetone phosphate also appearing, and glyceraldehyde 3-phosphate all appearing in the breakdown of glucose. They're all important molecules, and you notice they all have phosphates on them. Cells put phosphates onto sugars for a variety of reasons, but one of the reasons that they put the phosphate onto a sugar is to keep the sugar from leaving the cell. Okay? It turns out that sugars in their uncharged form can move across cellular transport proteins fairly easily, but putting a phosphate on them prevents that easy movement. And so it's a good way of constraining proteins inside of a cell. Okay, how am I doing on time? Let me say a couple words about disaccharides, and then I will move on. Okay, so disaccharides. As its name suggests, disaccharides are comprised of two single units of sugar. Okay? Now, there's one structure here I think you should memorize, but I don't think you should memorize it the way it's shown on the screen. Your book has decided to pick the stupidest possible structure it could show you for sucrose. Okay? So I have a better one I will show you in a second. The reason I don't like this one is they have decided to save ink and not show you how it actually appears, but instead bend this bond right here so as they can show it side by side. Well, what's wrong with that? Well, what's wrong with that is that means that carbon number 1 is right there, not on the other side the way we like to draw it. Carbon number 2 is there, etc. So you have to memorize this guy upside down. It's a dumb way to do it. So we're not going to memorize this structure, but we should know from this structure that sucrose is a disaccharide, one unit of which is glucose in the alpha configuration, the other unit of which is fructose in the beta configuration. And it's a rare example where two anomeric carbons are joined. Very rare. We don't see that hardly anywhere else. Now, if we look at the sugar on the right, we see that it's also a disaccharide. It's called lactose. Lactose is called milk sugar because it is the most common disaccharide found in milk. It contains a glucose and it contains a galactose. And you'll notice how the carbons are numbered. Okay, so in this case, the orientation is appropriate. We see carbon number 1 where my arrow is on the glucose, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Over here we have carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Okay? Now, this linkage that is here is described as beta 1, 4, meaning that the beta carbon of galactose is linked to carbon number 4 of glucose. Beta 1, 4 linkage. Notice carbon number 1 was an anomeric carbon. This is a glycoside because the hydroxyl on carbon number 1 has been altered. It's no longer a hydroxyl. This is a glycoside. This guy is a diglycoside, as I will show you in a second. This guy down here, maltose, is a glycoside. Okay? And again, we see alpha 1, 4 in this configuration. This guy up here is called an alpha 1 beta 2. And again, I want to show you this on a separate figure. But in each case, all three of the molecules that you see on the screen are all glycosides. They're all differing. They all do not have anomeric carbons. Okay? Okay. All right. So if we go to the next slide here, I want to show you one more thing, and then we'll take a break. And that one other thing is a very high-quality figure that I was able to obtain from my own hand. I drew this myself to show you how sucrose actually looks in solution. Okay? It actually has this fructose underneath. It has a glucose above it, as you can see here. And now you can see that alpha 1, beta 2. That's carbon number 2 in the beta. Carbon number 1's in the alpha. That's glucose on top. That's fructose on the bottom. Okay? Now, when you look at that, you can recognize that that is actually the way that sucrose looks. For reasons mysterious to me, I've found now a couple of textbooks that use this stupid designation of sucrose instead of showing you what it actually looks like in three-dimensional space. I'm not quite sure why they do that, because I think all it does is confuse the students. And that's supposed to be the job of professors. So, okay. Bad joke aside, that's a good place to take a break. Let's take a break for a couple minutes, and we will come back. I got to change that. Oops, sorry. Yep, excuse me, sorry. A little warm in here today.